Lecture 31, we're going to talk about Newton's second law in a little more detail, in a more traditional way. We're actually going to begin by talking about what Newton described as the quantity of motion. Okay? And the quantity of motion is what we now call momentum. Okay? It's represented by the symbol P, and it's equal to the mass times the velocity. Now, of course, since velocity is a vector, so is momentum. Okay? And this definition of quantity of momentum kind of makes sense, because if you think of the difference between, a very light object that's moving at a constant velocity, right? Like say, I don't know, one of those, a bicycle, right? That's moving down the road at 25 miles per hour. Yeah. That has a different quantity of motion than say a car traveling down the road at a constant velocity of 25 miles per hour, right? Because clearly you would rather be hit by the bicycle than the car, right? Yes. And so there must be something about its state of motion which made you come to that decision, right? Mm-hmm. Yeah. So this was Newton's definition. Now, if the change in the momentum is not equal to zero, then this means that there was some interaction. Okay? This is my symbol for implies. Okay? So if there's no change, if there is a change in the momentum, right, then that implies there's some kind of interaction. And this, of course, is what we talk about as force, right? So you'd say, well, if there's a change in the momentum, then there's a force. Now remember, Aristotle, 1,000 years before Newton, but more like 2,000 years before Newton, would have said, when he thought about motion, he would ask the question, what makes something move, right? Or really more accurately, what keeps something moving, right? Because in his world, right, if you were to, put a bicycle into motion, eventually it would come to rest. And so you'd think, well, what do you have to do to keep it moving? So if he had a definition of force, he would think of it as the thing that kept the bike moving down the road, right? Whereas Newton is interested in what creates a change in the state of motion. Remember, the first law, right, was basically that said that in the absence of an interaction of some kind, or in the absence of any external forces, right, there's no change in the momentum. If you're sitting still, you continue to sit still. If you're moving with a constant velocity, you continue to move with a constant velocity. This is this principle of inertia, right, that originated with Galileo. All right. So we can now say that the force is the time rate of change of momentum. Okay? Okay. And if I use this definition up here for momentum and consider constant mass, right? So if the mass is not changing, right, then this is just m times delta v over delta t, which is just m times delta v over delta t. And who knows what delta v over delta t is?
Acceleration.
Acceleration. So this is mass times acceleration, right? Which makes force, of course, a vector quantity. And experimentally, we observe that force is a vector quantity. Okay. Now, I've got a series of questions I want to ask along the way here. So, if the acceleration on a body is zero, are there any forces?
No.
Well, maybe I jumped the gun here. Hold off on that question because I need to add one more thing to this, right? I'm going to formally state that Newton's second law, what's called N2, basically says that acceleration is equal to the sum, this Greek sigma, uppercase sigma, we use to stand for sum. It means you add them up, okay? Of the forces, and inversely proportional to the mass, okay? And these are vectors. Sometimes you can call that net force, okay? So remember, forces are a vector quantity, right? If forces are a vector quantity, right, that means they have direction and magnitude, right?
Yes.
And so they will add by the parallelogram rule of addition, right?
Okay.
Yeah, remember the parallelogram rule of addition? If this is a force 1, and then I have another force in this direction, right, then we can think of this parallelogram, right? And the sum of these two bisects this parallelogram. That's a terrible So this is F1 plus F2, right? So another way to think about it is that force, adding like a vector, right, you can add the components, okay?
Okay.
So if you put a coordinate system on there, you can break it down into components. You can say, well, here's the force in the x direction, here's the force in the y direction, and then you can express the force in terms of those components, okay? And if you add two forces, their components will add, right? So now I ask the question. If the acceleration is 0, does that mean that there are no forces? Any ideas?
You think?
Well, let's just work it through. If we say acceleration is 0, that means that the sum of the forces divided by mass, and just multiply both sides by the mass, and anything times 0 is still 0, so we get that the sum of the forces is equal to 0. That's different than saying that there are no forces,
Yeah.
because forces are a vector quantity. They can add in a way, right? Here's F1. Here is F2, right?
Pardon me.
They're going in opposite directions, right?
Yes.
Let's say that their magnitudes are equal.
Okay.
The sum of those two forces is 0,
Okay.
okay?
All right.
You can think of this as, a tug of war between two people that are pulling with exactly the same amount of force, right? Not going to move one way or the other. It's just going to stand still, okay?
Okay.
Okay, so I want to quantify force, right? And so we have to define it. And since Newton invented it, it's named after him. And so the unit of force is called a Newton, okay? And we define 1 Newton as the amount of force, right? So let me just... It's the amount of force to accelerate a 1 kilogram body 1 meter per second per second.
Okay.
Okay? That's 1 Newton. So 1 Newton equals 1 kilogram times 1 meter per second squared. That is the definition of a Newton, and that is our unit of force. Okay?
Okay.
Now, that being said, we need a way to actually measure these forces, and I'm going to erase this. I don't think we need this anymore. And a good way to measure forces is with a spring. And so you'll find that with a spring, right, it'll have a relaxed state. Okay?
Okay.
I'm going to consider this a wall, right? So here the spring is in a relaxed state. If I pull on the spring, right, if I pull on the string, I'll call this position, the position of the end here, right? I'll call this position x naught, and I'll call this position x, okay? And this is not x, this is delta x, or the displacement, right? So if I pull on a spring, it stretches out, right? And so this point here at the end is now at a new position x. And so delta x is equal to x minus x naught, okay?
Okay.
It's the amount from equilibrium that we stretch it out to, okay? It's how much we change the length of the spring, I guess you could say, right? Make sense?
Yes.
It would also work for compression. You could compress it, okay? Squish it, and however far to the left you went, x naught minus that would be your delta x. And so you can plot, you will find, and this is called Hooke's law, you will find that for a large region, right, or for large displacements up to some point, right, that Hooke's law is linear, okay?
All right.
Which means that the force that you get is proportional to the displacement of the spring, okay?
All right.
And so with that, we can now imagine a force measuring device. If I place a block of some mass m on a frictionless table, I can attach it to this kind of spring scale, right? This will have a spring inside of it, and over here I'll have an end that I can pull, right? Apply a force, and it will have a gauge on it with tick marks all the way through. And as I pull on this, I'll have a little indicator which shows me how much the spring is stretched from equilibrium, okay? And I can measure that. So I can use this thing to measure force. I can first calibrate it by using, set this to be a 1 kilogram block. Now all I have to do is accelerate it to 1 meter per second per second.
Yeah.
And whatever I read on there will be 1 Newton, okay?
Okay.
And so now it's calibrated. And thereafter, I can put any mass on there that I want. And I can pull on it, right, and I can measure how much force I'm applying to it, okay?
Okay.
If I know the acceleration, then I can determine the mass. If I know the mass, then I can determine the acceleration, okay?
All right.
So this is a useful way to measure stuff, okay? And now we can define what mass is, and we'll do this with this dynamical definition of mass, right? So I'll say mass defined. I'm going to say that the mass of something, this will turn out to be, remember alpha from yesterday?
Yes.
Okay, so M naught and A naught, these are my standards, okay? This is my 1 kilogram block, for example, right? So all I need to do is, just like we did yesterday, or in the last lesson, is measure the ratio of the accelerations, right, using a standard mass, and I can write any mass in terms of that. And further, right, A naught times M naught, right, is F naught. That's my standard force, 1 Newton, right? And so now all I need to do is measure the acceleration, right, when I apply a 1 Newton force, which I can do with my calibrated spring, right? And that will determine the mass, okay?
Okay.
So does that make sense?
Yes.
Can you judge mass by size? If I look at something, here's a big thing, here's a smaller thing, and I look at it and go, oh, that thing, the bigger thing has definitely got a bigger mass.
No.
No, you cannot. Because how do we determine what mass is? Right?
Yes.
We apply a standard force of 1 Newton, we see what the acceleration is. That's how we figure out what mass is. Okay?
Okay.
Can mass be negative?
No.
In terms of this dynamical definition, right, I think you can see that you cannot have negative mass. That would be like having, when we had the two bodies pushing on each other yesterday, or in the last lesson,
Yes.
right? If two people push off on the ice rink and they end up both going in the same direction, does that make any sense? Would that ever happen? Well, that's what it would look like to have a negative mass, right? What about the idea that mass is defined as a quantity of matter? You've probably heard this discussion before, or heard this line of reasoning before, that mass is a measure of the quantity of matter. How does that compare with our definition of mass, right? Any thoughts on that?
Less accurate?
Well,
Entirely true.
in order for that to work, you would have to have some smallest mass, right? That everything else is defined in terms of, okay?
Yeah.
And so, you've studied chemistry, so you know that atoms are small things, and they're made up of protons, neutrons, and electrons, right?
Yes.
So you could say, okay, well, if we add up the protons, neutrons, and electrons, then we should be able to get the total mass of the thing if we know how many of each of those things is in the matter that's present, okay?
All right.
And so in that respect, it differs in that we have to know what's at the bottom, right? What are the things that make up the matter that we have to add up, right? When we get this quantity of matter, that means how many protons, how many neutrons, how many electrons. So we need to know that. Do we need to know any of that detail to use this definition of mass? No, we
No.
do not, right?
No.
That's why I called it a dynamical definition of mass, okay?
Okay.
I guess you could call the other one a static definition of mass. We say it's the sum of the protons, the neutrons, and the electrons. And that would be, a valid way to do things. There is a complication that arises that Einstein gives us that makes it not possible to actually use that to accurately measure mass. Turns out that you can have the same number of protons, neutrons, and electrons in some composition of matter and have a slightly different mass. But this is a complication I'm not going to go into. It has to do with relativity. But yes, we don't need to think about that. We don't need to take this reductionist view to define mass, whereas we would with this quantity of matter business. So now that we've got this idea of the scale, let's think about a concept related to mass and often confused with mass, and that is weight. Okay?
Okay.
Let's take our 1 kilogram standard, right, and let's suspend it from a spring. What are the forces that are at play here, right, if we look at this diagram, right? Let's first imagine that there's no spring. Let's take the spring away, right?
Gravity.
Right? We've taken the spring away. What's going to happen to this 1 kilogram mass?
That's gonna fall.
But more importantly, it's going to
Fall.
accelerate, right? And how fast is it going to accelerate?
At 10 meters per second.
About 10 meters per second, okay? So, and it's a 1 kilogram mass, which means that there's a force, right, which we're going to call weight, which is equal to 1 kilogram times 10 meters per second squared, which is 10 newtons, okay?
Okay.
Remember, 1 newton is 1 kilogram times 1 meter per second squared, Okay, so this is 10 newtons. Okay.
Okay.
Now let's put the spring back in. Okay. Where is the spring scale going to be? Where's the indicator? Well, remember here in the picture, I put the indicator there. Looks like it's like 5 newtons or something. Where is the indicator going to be on this one? If this is 0 and this is 10. Well, if we don't have the spring scale here, then we know there's a force of gravity, which is going to accelerate this 1 kilogram block at 10 meters per second per second. So we can think of the force because of F, the sum of the forces. There's only one force acting on it, right? And that is gravity, right?
Yes.
And it's accelerating at 10 meters per second per second. Thereby, Newton's second law says that the force is equal to the mass times the acceleration. Okay? There's only one force because we've only identified one force, that's gravity here. Okay? So the sum of the forces is equal to a single force, which is this gravitational force, right?
Yes.
And the magnitude of that gravitational force is 1 kilogram times 10 meters per second per second. Okay?
Okay.
10 newtons. And it's in the downward direction, so we now have a direction for it. So I draw an arrow representing this. Right? And the magnitude of this arrow is 10 newtons. Okay?
Okay.
Now, let me suggest that the spring is going to be applying a force in the opposite direction. Okay? I'm going to call this F sub S, F of spring. Okay?
Okay.
It is pulling up on it because you've had a spring before. You know if you pull out on it, it's pulling you back, right?
Yes.
So if I attach a spring to your earlobe, you'd be like, ow, right? It's pulling my earlobe. Okay?
Yeah.
If I put a spring in your mouth and told you to bite down, it's going to be hard because the spring is pushing in the opposite direction that you're trying to stretch it.
Yep.
Okay? That's the thing with these springs. If you try to stretch it out, it's going to try to pull you back in. If you try to compress it, it's going to try to push you back out. Okay? That's Hooke's law. So now we've got another force here though. When I put the spring scale back in, I've introduced another force. So now I have two forces. And so what can I say? But is there any acceleration here? If I hang a 1 kilogram block from a spring scale on the ceiling, does it accelerate? We know that the sum of the forces should be equal to the mass times the acceleration, but the acceleration is 0, right? So the sum of the forces should be equal to 0. What's the sum of the forces? Well, we've got to keep direction in mind here. If we call this the positive direction and this the negative direction, the sum of the forces is, well, I've got F sub S, which is in the positive direction, plus negative F sub W, right? Which I could just write it as minus. Minus F sub W, right? Because that's in the opposite direction. Okay, and that's equal to 0. So that says that F sub S, the force of the spring force, right, is equal to F sub W, which is equal to 10 newtons. So this guy is going to read, its indicator will be right there, be pegged out at 10 newtons, because that's as far as I want with my scale. Okay? So here we've applied Newton's law to study this simple system of measuring a mass with a scale, a spring scale. And this is how we reason through it. Okay?
Okay.
Does that make sense?
Yeah.
Yes.
Okay. Let me just do real quick one example of force is a vector. Okay? Force is a vector. And so let's imagine we've got a post. This is a stump. And we want to pull that stump out of the ground. I could have a tractor, right, which is pulling with some force 1 in this direction. And then another tractor, which is pulling with force 2 in this direction. And let's say that those directions are orthogonal, right? They're at 90 degrees to each other. Okay? So F1 is pulling with a magnitude of, let's say that's 1 Newton due north, right? Use a compass. And the other tractor is set up to pull with 1 Newton due south. No, not south. That would be bad. Due east. Okay?
Okay.
What is the resultant force? Well, we can treat this, right? We've got, this is my 1 Newton in the eastern direction, and this is my 1 Newton in the northern direction. Should probably make it a little more equal. Then Pythagorean theorem, right, gives us the net force, right?
Yes.
And so that will be equal to the square root of 1 squared plus 1 squared, which equals the square root of 2 newtons. That's a terrible N for newtons.
All right.
So just like with velocities, we can do it the same way. We can even define the angle, right? So that's the magnitude of the force, but which direction is it going? Well, the angle, theta, right, So we know it's somewhere in this direction, right? What is this angle, right? Figure out what theta is. Well, theta is just equal to, the tangent of theta is equal to the opposite over the adjacent, which means that the angle theta is the arctangent of 1 divided by 1, which is just 1. Whose tangent is 1?
A 45 degree.
45 degrees. 45 degrees, they're equal. And so when I divide them into each other, I get 1.
Yes.
So this angle is 45 degrees. So that's 45 degrees. And the force is the square root of 2 newtons. Okay?
Okay.
So I guess you'd call that square root of 2 newtons north by north, or northeast. Or due northeast. I'm not sure. I'm not a compass person, to be honest. So that's the vector nature of a force. Okay?
All right.
I want to conclude with just a couple more questions. Let's see. All right, so you see a car rounding a curve, right?
Okay.
Is there a force present?
Wait.
Car
Yes.
is going around a curve. Is there a
Yes.
force present?
Yes.
There must be, right?
Yes.
Yeah.
Because there must be an acceleration.
There's an acceleration. It's changing its velocity, okay? If a force, a known force, call it F1, we know its magnitude and direction. If it acts on a body, and this is all the information you know, can you tell which direction the body will move?
Yes.
Really? Let me ask you the next question. If a known force, whose magnitude and direction I know, acts on a body that is initially at rest, can you tell which direction the body will move? Do you see the difference?
Yes.
So the body that's initially at rest, right, that means that all the forces are balanced out. If it's at rest, there's no acceleration. That doesn't mean there's no force. There could be a couple of forces that are balanced out, and therefore it's not accelerating, right?
Yes.
Yeah.
But it's initially at rest. So if I apply a force that has a known magnitude and direction, I can tell which way the body's going to move, right? Because if this thing is initially at rest,
Yeah.
whatever these forces might be that are all balanced out, right? And I apply some known force, F, right? It's going to move in the direction of the applied force. That's what Newton's law is telling us. Newton's second law, okay?
Okay.
If I don't know about the state of the body, if I don't know that it's at rest, maybe it's accelerating. Well, if that's the case, then we have to do a vector addition, like we just did, of all the forces involved to see which direction it's going to go, okay?
Okay.
Does that make sense?
Yes.
Okay. So it gets a little complicated. Solving some problems, you'll begin to see how to do these things. We're going to do one more lecture, and it'll be on Newton's third law, because this is easily misunderstood. Okay, and we have to be very careful to apply it, right? In the meantime, you might think about the following. You remember that Newton's third law says that for every force there's an equal and opposite force, right?
Yeah.
Yes.
Well, if that's the case, and I have a horse pulling on a horse cart, but the horse cart, of course, is going to be pulling back on the horse, equal and opposite. How does the horse cart ever move? Right?
Yes.
So give that a think, and we'll talk about it when we talk about Newton's third law in a little more detail, okay?
Okay.
In the next lecture, lesson.